All right. Hello, Node Congress. I am James Snell. I'm going to be talking to you a little bit about async local storage and how it works. It's an API that's been around in Node for quite some time now, a number of years, and it's starting to be picked up by a number of frameworks, Next and a few others, and it's being implemented in a variety of runtimes like Dino and Node and Workers and Bun. So I kind of want to talk about, how it works. Just kind of dig into the covers a little bit so you can kind of get an understanding of what's going on. For some background on me, because I'm James Snell. I'm a principal engineer at Cloudflare. I work on the Workers platform. I've also been on the Node Technical Steering Committee for, oh wow, almost a decade now. I've been contributing to Node since 2015. And I am the co-chair and one of the founders of the WinterCG. That's the Web Interoperable Runtimes community group, where we're focused on getting all these different runtimes, Bun and Dino and Workers and all these different things together to talk about standardized APIs across the board. So that's me. If you've heard of me before, it's probably because some of the things I've contributed to Node over the years, things like the WhatWG URL, web crypto implementation, web streams implementation, that kind of thing. But yeah, let's get into it. All right, so if we look at the async local storage documentation on the Node website, this is the very helpful introduction that it gives, talking about these classes are used to associate state and propagate it through callbacks and promise chains. Doesn't really do a lot to help us understand what this API is doing under the covers. And if you haven't noticed, just Node docs in general don't do a great job of explaining things. So we're going to dig into the details just a bit more, explain how this works, how it all comes together. All right, so let's look at an example. This is kind of the canonical example I like to use for async local storage. Let's imagine we have a function. We have this export default function right here. This is the kind of the worker's way of exporting a function handler. We have this async fetch. We want it to do something, and eventually we want some logging to happen in here. So we have this log function that logs a message. Think of it as essentially as just a console log, that kind of thing. And what we want to do is define a request ID that gets logged with the message whenever it goes out. Now, kind of the traditional way of doing it before async local storage, the way we would have to do this is, we'd come up with the request ID. So here we're using the const ID equals crypto random UUID. And we actually have to plumb that ID through all the different functions that need it. Or that end up in a log statement. So here we have to modify do something and do something else to take that request ID and forward it on to log, even though the do something and do something else have, don't do anything else with request ID itself. So, this gets a bit complicated if these functions that you're passing this through are in some other library or some dependency in your code. Or if they're, or if they're doing complex asynchronous tasks, that kind of thing, it becomes kind of awkward to have to modify all of these functions just to pass this ID along in order to get it into the log statement. So what if there was a way that we could just say, here's the ID, whenever log runs, use this ID, but not have to be forced to pass that along through all the different layers of functions and stuff that we want to call. And that is what async local storage allows us to do. With async local storage, we can create this holder, this request ID equals new async local storage. This is the container, and we can specify in our fetch handler that hey, we want to run with this value. In this case, it's our request ID, this random UID. We want to run this code with that value set, right? And notice what changes here to do something and do something else. Don't have to know anything about the request ID at all. They don't have to pass it along, accept it as an argument. When log is called, it doesn't have to tell it, okay, what request ID are you running under? When log is called, when log is invoked, it will go to that container, that async local storage container, and just say, hey, get the value that's currently set for this when I'm running right now. So it kind of gives a really simple way of just kind of, hey, store this value later on in some other layer. We want to get the value. And notice that we're doing this past awaits. So this is happening asynchronously across multiple steps of the of a promise branch. So it makes it a lot easier, especially if these do something and do something else functions are coming from some dependency that you have no control over, that you actually can't modify. This way, you can actually set that context and retrieve it later without making any modifications to the to everything else. So that's the advantage of async local storage. But what is happening under the covers to allow this to work? Let's get into that. All right, so we have this concept of a storage frame. Now this is, in Node, the storage frame is really more of an abstract concept. In some of the other runtimes like workers, we actually have an internal class called the async context frame. And basically what this is a map, right? All it does is store key values. You specify a key, specify a value, whatever. So it acts like a pretty simple map. How that relates to async local storage is that every async local storage variable, every instance of that is a key. And at any given time, that key, that async local storage instance, has a value. Now, initially, that value is always undefined. But whenever you call run, it sets that value. Okay? And then whenever you call ALS get store, it retrieves the current value in that map. So think of that, just this frame that is essentially just a map. We could also just call this, the async local storage map, right? Okay. Importantly, there's not just a single frame in the application, all right? Storage frames are immutable. We use a copy on write strategy. So basically, whenever we set a new value for a new async local storage variable, we actually copy the existing frame into a new instance and then set that value there. This is very important for performance, and we'll get into exactly why this works and how this works in a few minutes. But it's just important to understand that once a storage frame is created, that instance should remain unchanged. It is immutable. And what that allows us to do is anytime we want to reference that frame anywhere along in that promise chain or that async context flow, we can actually always retrieve the value that was set on that frame, on the relevant frame that was set, even though we might have any number of frames that have been copied since then. We'll go into a little bit more detail on this, but the point of this is just to show it. There's very simple primitives that are used here. A map, copy and write, right? We're just setting these values. It's just key values. That's it. Okay. So initially, when you start your application, the initial frame, there's always a frame. There's always going to be a frame, a current frame. That is initially empty. It has no values in it whatsoever. All right. The first time we call ALS run, and ALS being async local storage, first time we call run and we specify a value, what's going to happen is that initial empty frame is going to be copied into a new instance. And then in that new instance, we're going to set that ALS as the key equals this value that we passed in, this 1, 2, 3 in this case. And notice that when we're running inside that, inside ALS run, that new frame that we copied becomes the current, all right? That initial frame still exists. It's still there, all right? But that new frame becomes the current frame. And when we call ALS2, another instance of async local storage, we call ALS2 run, we end up copying that second frame into a third, and then setting that ALS2 value in addition to the ALS123 that was already there. So in this case, we have 3 storage frame instances now. ALS run has been called twice within, right? Inside this second ALS2 run, it's this third frame that actually becomes the current. The other 2 still exist, right? They haven't gone away yet. All right, so we're essentially creating a stack of what these frames, these copies of these frames, and each copy is setting a new value in that map. All right. Okay. So there's always a current storage frame. Run stores a reference to the current frame, copies the current frame, sets the new value, sets that new frame as current, runs that callback, and then restores the original frame. And this code right here is not the actual implementation. This is just a kind of a pseudocode implementation of this that shows the flow. Okay, so when run is called, this is the ALS run, we get the current frame. All right. Then we copy that current frame. We set that value. This in this case is the async local storage instance. So we're using that as the key. We set that to this value, and then we set that new frame as current. Run the callback, and notice in the finally, so whether the callback errors or not, whether it completes correctly or if there's an exception, we're still going to come back and we're going to restore the frame that was current when we started the run. Right, so we're basically just swapping these things in and out as we go through and run this code. Okay. All right. So is that it? Is it really just a map? There's a bit more to it than that. So we have these frames. Like I said, every time we call run, we go out and we copy this frame, we copy this map, add a new value, set it as current, all these kind of things. But that doesn't quite give the entire picture, because what we also have to know is, like, how are we setting and resetting these things so that in every individual promise or every individual async activity that happens, the right frame is being used at any given time. So let's talk a little bit about how a promise works. These are the internals. And I'm greatly oversimplifying this on purpose, but this should give a little bit of an understanding how this flow and what's going on under the covers. All right, so we have a promise, right? And inside a promise, we have basically four values. There's more than this, but like I said, I'm oversimplifying it. We have a status, which is the promise is either pending, resolved, or rejected. We have a result, which is either the value that was resolved to or the exception. And we have a set of reactions, either resolve reactions or rejection reactions. There's also finally reactions, but I'm going to ignore those for now. And what those are arrays of tasks, okay? For each of those. And tasks these are like the things to do after it resolves, so the things to do after it rejects. So these are the things that are set with then or catch or finally, that kind of thing. Okay, so the promise, that is that structure. Also, we have this promise resolver, which is the pair of functions, either the resolve or the reject, that modify that state. And then we have this micro task queue scheduler that actually runs the tasks. Okay, so we have some bit of code. It calls resolve to resolve that promise. We're going to set the status to resolved. We're going to set the result to whatever value it is. And then we're going to take those array of tasks in the resolve reactions, and we're going to pass those off to the micro task queue schedule to run. And then at some point in the future, we'll tell the micro task scheduler, hey, run all of the tasks that you have collected up to this point, and the scheduler will go through and just start iterating through every single one of those tasks and say, okay, run this one, run this one, run this one. All right, that's an important step. Okay, so we have the promise, we have the resolver, we have the scheduler. Resolver sets the status of the promise, updates it, and causes the microtask scheduler to receive a set of tasks to run. All right. Notice it says tasks and not functions. When you call .then on a promise, you're passing it a function, right? When you call it .catch, you're passing it a function. And these are callbacks that are invoked. A task is not quite the same thing. A task is a bit more than just the callback. The task has the function, right? And then it has a resolve and reject function attached to it, okay? And it is used to perform the next step in a promise chain, okay? So when the scheduler receives this thing, it's going to look at this. This resolve and reject is the resolver for the next promise that this task represents. So we took one promise, resolved it, and we have another set of another task then as a continuation, right? That is also represented by a promise. This resolve and reject, this task is the resolver for that second promise. Bit confusing. We don't need to go into all the details there. Like I said, I'm oversimplifying this quite a bit just to break it down. But this is what a task is, right? It's just a function, a callback that resolves another promise, okay? So, we can see that here, function, run task. This is what the scheduler would do, okay? The scheduler's going to run this task. It's going to run them one after the other. What it's going to do is, within a try catch, it's going to try to run the function. If that succeeds, then we're going to resolve the next promise with the result. If that errors, we're going to reject the promise with the error, okay? Pretty straightforward. Calling then, calling catch, like I said, creates these tasks. So this is essentially what is happening inside that promise then, or promise catch, is we create another promise, we push the reaction onto that, into that promise reaction array. We're creating this task as the function resolve and reject, and then we're returning the new promise that was created. Okay, pretty straightforward, pretty simple. All right, what about async context? Where does that play in all of this? Okay, so what we do when we call, again, this is looking at the then and catch. When we want to create that task, we have to add an additional field. And this additional field is a reference to whatever the current storage frame is. All right, so like I said, there's always a current frame, always. Initially, that's empty. But every time we call ALS run, we create a new frame and set it as the current. So when I call promise.then, right, it's going to grab whatever the current frame is, a reference to that, and store that reference in the task itself. All right, so the task is now function, a resolve reject for the next promise, and a reference to the current frame. Okay. Now, when we run the task, again, this is in the scheduler. What the scheduler is going to do is say, okay, I want to get the current frame, whatever the frame is right now, before I run this task, and it's going to store a reference off to the side. And then it is going to take whatever frame, whatever storage frame that task is captured, and set it temporarily as the current. Okay, that's what we have here. Const current equals current frame. That's where we're setting the current one off to the side. We're replacing that with whatever one the task is captured. Then we run the function. Right. Again, this, if the result succeeds, we set the resolve the next promise to the result. If it rejects, we reject. And notice in the finally, so whether it succeeds or fails, in the finally, we restore the current frame that was captured. So every time we run a task, grab the current, replace it, run some code, restore the current. Okay. So every time it runs, we're replacing this thing so that when task function runs here, it's going to see the frame that the task captured when the then was called, or when the catch was called. That's the one it's going to see as the current. So essentially, we're just swapping things in and out. Okay. All right. Sum up. There's always a current storage frame. Initially empty. Every call to ALS run creates a new frame that's a copy plus the new value. Calling ALS get store only looks at the current frame. Right, so it says whatever's current, give me the current value for that, if anything. Every call to promise then, finally, catch creates a new task that captures a reference to it. When a task is run, it is captured. Its captured frame is temporarily set as the current, and when there are no more references to a frame instance, that one frame can be garbage collected and freed. So, for instance, like I said, there's initially an empty one. We call ALS run once. It creates a new frame and runs some code. If nothing in that run code captures a reference to that frame, so if we don't create another copy, if we don't create any tasks, there's nothing holding a reference to it. It's just another JavaScript object, which means it can be garbage collected and freed, so we're not holding on to any memory, that kind of thing. So it's important that there's like I said, I'm oversimplifying things quite a bit in here. There's a lot more going on under the covers, but this kind of gives you the basics, a high level of how all this works. What about something like set timeout? Set timeout's not promise-based. How does that work? Well, same way. When set timeout is called, we capture a reference to whatever the current frame is. When that function is actually invoked by the timer, the underlying timer, we restore that, right? But first we capture the current frame, set it aside, restore the frame that we reference that we got when we called set timeout, invoke the callback function, and then restore the frame. So we're just the entire time we're just kind of swapping out these references so that the get current frame will always reflect the right one. All right, Node does things a bit differently. Node's implementation, it's older. It uses async hooks and promise hook APIs. It's a lot slower. Frames end up getting copied every time a promise is created and every time an async resource is created, like a timer or next tick, rather than every time ALS run is called. And you can imagine that in an application that is creating tens or hundreds of thousands of promises, copying this frame on every time a promise is created gets very expensive from a performance point of view. We are looking at improving this. And other runtimes like Workers uses a model that's closer to what I described in here, where we're only copying every time ALS run is invoked. We want to make Node's implementation like that, and we're using an obscure V8 API that's used in workers, using Chromium, that makes all of this a lot easier, and it's going to underlie some of the new things that are coming. We'll talk about in just a second. So the Node implementation does work a little different. It's a little slower. But we want to change it. We want to update it and get it and basically modernize it. What is async context? Async context is a new TC39 proposal. TC39 is the committee that actually standardizes the JavaScript language. The proposal is basically to add async local storage to the language itself, rather than it being this non-standard API. But they are changing it. They are changing the name of it. Some of the details will change. So right now, in order to use async local storage, you import it from Node async hooks. And this is, whatever platform you're on, whatever runtime you're on, you access it the same way. You're importing it from this Node async hooks module. You create it with the new async local storage constructor. You have get, store, run, right? With async context, it's for the most case, it's going to be a drop-in replacement. A few details change. You don't have to import it. It's going to be a global. Get stored just becomes get, right? So request ID get. Request ID run remains the same, exactly the same way. So if we look at the two, very minimal differences between these. There are some other differences with async local storage API, some things that async context will not pick up. I'm not going to go into those right now. They're not that important, and they're experimental features on async local storage anyway, so it's not worth it actually going into. This here are the pieces that you really need to understand. Okay, and that's it. So I hope that really helped. Just kind of draw back the curtain just a little bit, so you can understand what is happening under the covers with async local storage. Again, just grab the frame. We modify the value by copying it. We're just swapping those things in and out. And yeah, I hope that helps. Hope you enjoy the rest of your conference.